we sell this, but it's going to be predominantly a lab class. We'll probably only have 2 tests. So we'll probably have a midterm and a final just to cover information and just see how much we can do. So the process of that class is you're going to come in and you're literally going to wire the PLC up on one of these modules right here, which is really neat. And then we'll let y'all hook it up to the Allen Bradley, up to the Festo line, and just write simple programs to make actuators move and read input from switches. And then we'll look at taking the Allen Bradley programs and convert them over to compatible Siemens. And one of the things that they don't talk about, and this is not covered in the book at all, and I was telling Thomas about it, is sometimes it's very important when you switch your PLC into the run mode to go out there and initialize your ports from somewhere to start, right, without trying to hit a PLC. So both the PLCs that we deal, and I imagine it's pretty popular. The only ones I'm dealing with is the Allen Bradley and the Siemens. I'm sure there's a lot of other PLCs out there. But what they provide in the status register is what we call a first scan bit. And the first scan bit I have to figure out which one it is. I'm sorry, Sarah. I have to go back and look at it myself. But the first scan bit, when your processor or when your CPU switches from run to, when it switches to run, what it does is it enables an input contact called, Allen Bradley calls it the first scan. They call it first pass. And then Siemens calls it first scan. And it took me a long time to figure it out in the Siemens package. So I'll get you the right bit here so you can make a note of it as soon as I find it. We'll try to bring up the one that's got the it's got all the comments and everything in it. And then we'll look at that, and then we'll pop up the one that I've been working for on Siemens, and make sure you understand that. The Allen Bradley, it's just a bit that's in the status register. So it's over here in the status register. And then the Siemens, it's a bit that you have to program. You have to initialize it or set it up. So when you bring it in, it's automatically going to put this comment called first pass. I didn't put that in. It's S1/15, which is what we call the first pass bit. So all we can do with the first pass bit, so you can see what they're doing, is the first pass, it's going to come out here and do what? It's going to run a subroutine. It's going to run subroutine 4. And what it's going to do is it's going to go out there and fill all the bit registers using index addressing with what? Plus the 4 0. What it's going to do is going to clear out these memory addresses for it. These are the ones that they use for the bit files. And then what it's going to do is going to fill output 0, the whole word, output 0, word 0 with what? I'm going to fill it with 0. Don't make sense? Everybody understand that? So what it's doing is turning off all the outputs, putting all the outputs to 0. And then what's it doing? It's filling up all the bit files that it's using for all the internal relays. So this guy's got a ton of internal relays. So all these bit files out here, all these Bs, these are all internal relays. But what he's doing is right off the bat, I said it could have been a she that wrote this, just as good as the guy. What it's doing is going out and just clearing out everything and getting it ready for it to come up and run, right? So Alan Bradley calls it their first pass, and what bit is that? It's inside the status register. Yeah, 115, so we'll see if we can see it. I didn't see it in here. So scan time. Here's the math operations. Here's channel 0 debug errors. So they don't show it. They don't show it inside this table. Oops, sorry. So they don't show it inside the status register that they give us access for. And this is just something you have to know. And the problem is, when I was trying to convert the programs from Allen Bradley PLCs over to Siemens, it was real hard for me to sign something like that. But when you get in the manuals, if you scan for first scan, so Siemens calls it first scan. I think it's got an underline. Allen Bradley calls it first pass. And what does these bits give you the ability to do? Set everything up as soon as you switch the PLC to what? To run. And it's only one scan. That first scan, the first scan it goes to that ladder logic, it comes up and do that. Now, of course, they're going to a subroutine, which would be good. But instead of trying to do everything you set up, then what it would do is it go to a subroutine. And so now, when I go up on the front panel and hit the reset button, guess what it does? It runs this same subroutine. So remember, you can use multiple subroutines in different portions of the program. And we know now that we can have subroutines call over subroutines. And what do we call that? Nesting. So it's very popular using subroutines. Because what do subroutines allow us to do? Well, first of all, it lets us repeat runs anywhere in the program. So instead of me go back and rewriting all this stuff in my program, I can if I keep repeating the same thing, I can do what? I can put it in a subroutine, right? You understand that? And then I can pull it out one time. A perfect example, of course, is Windows. How many applications in Windows supports print? A lot of them. Why would I have to include that code every time in my application? Wouldn't it be nice if we could set up a subroutine that handles printing for Microsoft applications, and then every Microsoft application I wrote in, if it needs to print stuff, it can do what? It can jump to that subroutine. Microsoft calls them data link libraries. So if you turned on file extensions, if you could see file extensions on your computer, most people turn off file extensions on their computer because people don't understand extensions, right? So if we was to look at C:, and start looking at our program files, and then start actually looking at programs, then we should see a lot of DLLs. So these are all data link libraries. A file name under Windows is made up of two parts. It's made up of a file name, and then it's made up of what we call an extension. The extension identifies what type of file it is. So down here, readme.txt identifies that as a what? Text file. Now what we can do is we can set up what we call an association, which means this is not an application. This is a file that an application uses, right? So what we can do is we can set up an application. So when I come up here and double click on this guy right here, if it's got an association set up to it, then it'll automatically bring up the application. So it automatically brought up an application called what? Notepad. And we call those file associations. So every once in a while you'll double click on a file and the thing will pop up there saying there's no program associated with this thing. Have you ever seen that? Now you got to be real careful because usually it's got a check mark down there that says that you want to set this as the default, and from then on it'll use that application. So most of the time when you install an application on your computer, like Microsoft Office, it automatically sets up the associations for you. But all these DLLs, every one of these DLLs, what are these? These are subroutines. That's all they are. And so what happens when I load that application in, it goes out there and automatically loads these subroutines for you that you can use. And you can see, look at all of them. Data link, so DLL, 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 DLL. So what's happened is any application that needs to use that data link library, instead of you trying to do what? Instead of you trying to write it, PLCs, 500 does not support it, but most of your new PLC supports what they call libraries, which would be where you could put these what? You could put the subroutines in there, and then you could tell your PLC to go out there and load the subroutines, which is pretty good. So let me bring in the Siemens program. Another thing I like about Allen Bradley is Allen Bradley saves their files, all their programs in a single file. Siemens spreads it out over a big file. And it's real hard to figure out where the program's at. To me, some of y'all might figure it out. As soon as you do, let me know. So normally I just open mine up with the application that So what happens when you load in the field software? What it automatically does, it comes up and keeps the path to all the ones that you're working on. So Siemens calls theirs they don't call it the first pass. I think they call it first scan. So this is the adaptation of that same program, but it's over to Siemens software. They don't call their original block, they don't call it ladder, they don't call it ladder 2, they call it ORG. I'm sorry, they call it QB1, but what can you do? You can come back and do what? Yeah, you can give it a name, or a symbol. So this is the same diagram under step 7 software. So here's my subroutines out here. And here's and they don't call them rungs, they call them that. So they call it first scan. And then what you have to do is you have to set it up to one of your bit files. So Siemens calls their bit files M instead of B, M. And it's considered, if you don't tell it, it's considered to be an 8-bit bit file. So this would be this word number, this byte number, and then this would be the bit number. So this gets people confused that's coming from Allen Bradley, because if we see the dot, we think it's a whole word. But in Siemens, the dot identifies a bit. So that's a big difference, right? What Siemens does is you identify the link by changing the M. So if I use MW, then that's going to be word, right? If I use MD, that would be a double word, right? You understand, or what we call a long one. But what you do with Siemens, you specify the length of the file that you're dealing with by putting little designators in there. That makes sense. If you just use a single letter, then it's going to be a bit file, right? You understand? Or MB would mean you're dealing with the whole byte. M means you're dealing with a bit, right? You understand that? And then we put what bit we want after the dot. So that's just a little different. So they call theirs first scan. So if you wanted to set it up, get on the Siemens PLC. If you wanted to set it up, learn how to set it up, and come out and just search for what? First scan, and it will take you into the magazine. Right? Because you have to configure this. You have to assign it to a bit. One of your bit files. But this does the same thing. And the subroutines are a little different either, too, because it puts it out here where in Allen Bradley, if it's over here, we consider it to be an input, but that's not true on Siemens. So this is going to a subroutine called file C2, which is a subroutine file, and we gave it a name. So it's pretty similar. And like I said, I didn't have much problems adopting. There was a couple of things I had problems with trying to figure out. But the first thing I had problems with trying to figure out where to get this guy at. When I searched for first pass, which is what Allen Bradley called it, it didn't show up. So this is Siemens, but you see it's pretty what? Pretty similar to Allen Bradley. Huh? Oh yeah, we'd have to come back and look. The problem that I had, and I tried to find this on the internet, is so this is the so here these are all bit files, right? M2, so that would be the second byte, bit 5, second byte, bit 1. This would be the 0 byte what? Yeah, 0 bit. These are all set and reset. That's like Allen Bradley's latch and unlatch. So these would be repetitive relays. Siemens calls them set and reset. So that was pretty easy to figure out. The outputs, though, they call what? Yeah, so the outputs they call Q. And then it would be a bit, since I don't put a byte. So we can update bytes, we can update words. So if you don't put a letter in here, then you're just going to update a what? A bit. And this would be word 1, bit what? Bit 0. And that would be an output. Allen Bradley, Siemens uses Q for output, where Allen Bradley uses O. Y'all's probably run into that problem yourself, where you enter a 0, an O for a 0, or a 0 for an O, right? You understand? You're trying to figure out why you got an error. So Allen Bradley Siemens with a Q for the output. So this would be actually an output port on my PLC. It's 6.5% sign up there. I don't know why, but it does it. It'd be Q. It would be the first byte, right? Understand? Not when I say the first byte, byte 1. It would actually be the second byte because we start with what? 0. So this would be a byte 1, bit 0. Would be that output. So this is the same program, and I got the PLC at home right now on one of these, and I'm gonna take it over there tomorrow and plug it up and say a little prayer and see if it works first time. Highly unlikely. This rung right here, the auto line is like 38, 39 rungs long. So, odds are keying in all this stuff, odds are it's going to be highly unlikely that I did all of it without making an error, right? So we'll go there and plug it in and see what happens. So we talked about bit shifts left and shifts right. Shift left and shift right. Everybody okay there? Any questions there? We talked about jump subroutines. We talked about MCRs. We talked about the actual showed y'all true each stop button, right? Everybody okay there? Any questions? The last man will forever hold your peace, right? Talked about interrupts. I'm working on a program for y'all that I'll have to show y'all probably next class. And we'll demonstrate it on the 1100. So what's the next chapter in the book? Data handling instructions. So what type of things that we might want to do to just handle data? First of all, we need to have the ability to move things around, right? You understand that? One of the primary tasks of a computer is just moving things around, getting information to your display, on your computer, moving data here, moving data there. Plus a lot of things that we deal with. Humans, we have very hard difficulty, or a lot of difficulty with binary. So what does this computer right here understand? It understands binary. That's all it understands. All my programs understand is what? Binary, right? Understand that. But I don't understand binary. I understand what base? Decimal. So that means if I'm keying in information, if I've got a touch panel and I'm trying to read the revolutions per minute of a motor, if it gave it to me in hexadecimal or if it gave it to me in other base, I have no idea how that's happening, right? You understand that? So we got methods that we can convert from BCD to binary, binary to BCD, and all that kind of stuff. That's in here also. So moving stuff around, clearing stuff. So we have the ability to clear stuff. We have the ability to fill groups of memory. We have the ability to pull from groups of memory. So we've got a lot of things that we're just going to manipulate data just to move things around. And this also covers playing around with that world famous stack, right? So what's a stack? No, but well, not only subroutines, but the microprocessor sometimes has to have access to a group of memory without you basically ever saying, I want to put it here. You just set up a base, a stack, and then you can push stuff on that stack, right? You understand? If you need it, instead of me trying to set up addresses all the time, I can put stuff on the stack, I can get stuff off the stack, or the microprocessor or the processor can automatically stage stuff on the stack. So when I have an interrupt, what's it going to do? Well, it's got to go off to a predefined program, but when the interrupt's over, it's got to know where. It's got to know how to get back to where it came from. When I jump to a subroutine, what's it got to know? I mean, I can go all through. I can nest subroutines, but what does it got to have the ability to do? It's got to have the ability to do what? To return all the way back to the original application. Where the processor saves that information on is a section of memory called a stack. And what we do is we set up what we call a stack pointer. We just say, okay, we set up a stack. In machine code, we would do that. The PLC, the location of the stack is already identified. And what we can do is we can put stuff on there and we can get stuff off, right? You understand? So we have instructions that automatically use the stack. So interrupt instructions interrupts automatically use the stack, and subroutines automatically use the stack. But then I've also got the ability to save stuff on that stack if what? If I need to. Everybody understand that? So we'll look at some of those. Use PLC instructions to move data from one register and this guy uses registers all the time, which I really, really hate. We're going to move them from one data file to another data file, right? You understand? From input data files, output data files, we can get them from input data files. So your S register, that is a what? That is a register. That's inside the processor. All these flags that we talk about, that's inside the what? The processor. But we do have an R6 control register that we can also use as a sort of a status register, but that's going to be a data file. So this guy uses register a lot. What we're going to talk about is data file. Create stacks for storing and retrieving data from the PLC. So this is going to be a user stack. Move data between tables, use PLC instructions for number system conversion. Read, storing, retrieving, and writing data on ports and registers, moving and copying data to another data file, converting data to different numbering systems, performing a logic operation on data. So the instruction we're going to be looking at is move with mask. So the move we're already familiar with, right? What does the move allow us to do? Take one data file and put it somewhere else. Now remember, your inputs are data files and your outputs are data files, right? You understand? So that means using a move instruction, I can actually bring in a whole word of input information, and I can transfer that whole word of input information to an output data file. Everybody understand that? So we have the ability to do a lot. The move with mask, this uses an AND mask. So what it will do is it automatically AND mask a move. So if I was bringing in a word off an input port and I only needed the lower 8 bits, then I could do what? I could strip off the other 8 bits, or vice versa. Or if I needed the middle 4 bits or whatever, we could come up with that. Your FIFO and your LIFO, first in, first out, last in, first out. So how we get information off a stack depends on whether we're first in, first out, last in, first out. Does that make sense? Well, we'll look at it. Copy, which is very important. Fill, which is pretty important. Convert. One instruction that the guy left out is we do have a clear instruction. The clear instruction works on one word of memory, where the fill instruction uses it can do what? It can work on multiple words. Everybody understand? Sometimes simple called a pointer. We talked about what's the 4 addressing modes this processor, this thing uses, are available to us. Let's go the way we learned them, though. That's good. You're right. Well, we learned, first one that we learned is immediate. And what's immediate addressing? Huh? Yeah, the number is actually part of the instruction, right? So that would be considered a constant, right? Then we learned direct addressing. I'm not going to put the address in. What's direct addressing? Well, we identify a location in a data file where the information is either at or where we want to store it at. So if I come up here and I say N7, and then I come up here and say :0, then this is what? This is direct addressing. So what in direct addressing, we indicate the data file that we either want to get this information from or we want to put that information in. Everybody understand that? So if I come up here and I say N0/1, what addressing mode would that be? Well, that's going to be, that's direct addressing. No, but it's direct addressing because we're specifying the location of this in a data file. So some people believe that when I read an input, I'm actually going out there and reading that input port. That is false. What we're doing is we're reading a data file. Okay, you understand that? So, Logic Pro does okay with this. And when I update an output, I'm not sending information to the output. I'm sending information to a data file. And then the PLC scans that data file, and if it sees a 1 in the bit location, it turns that output on. If it says a 0 in that location, it turns that output what? Off. Y'all understand? So here's the data files. So here's the data files, input, and it's input 0, right? Everybody okay? So this is what it updates if I tell it to turn on an output. My program is not turning on the output, it's putting a 1 in this data file. And then when the PLC scans, all it scans is these data files and the whole word at a time. So it's basically updating all the outputs at what? At one time. Anything that's a 0 is going to do what? It's going to do what? Turn them off. Anything that's a 1 is going to turn them on. And when it goes out there and reads the inputs, what does it do? It goes out there and reads that input data file. So if I come up here and press a button, then what's it going to do? Well, it's going to put a 1 in the data file if it's pressed. If it gets back a voltage level, it's going to put a 1 in there. And if it don't get a voltage level back, it's going to put a what? A 0. Everybody understand? So data files. So we're using immediate direct addressing anytime we address a certain input port. Then we have indirect. What's indirect? This guy here. We're not going to use. But what is indirect? So direct addressing. How do I specify direct addressing? I just put the register number in there instead of the operand. How do I specify immediate addressing? Well, I put the operand in the instruction instead of an address, right? You understand? So what's indirect addressing? So what we're doing is we're getting the address of the operand indirectly from a register. So here I would come up here if I said N7 colon 0. Then what it would do is it would go out to N7 colon 0, which is an address. And if it equal 53, then the address of my operand would be 53. Okay, you understand? Now what's nice about this? Well, we can manipulate that data register. I can't manipulate direct because direct is inside the instruction. But I can manipulate a data register. So I can literally go out and change the contents of N7 colon 0. And what would that do? Well, that next time the instruction ran, it would use a different address. So the advantage of indirect addressing is we have more flexibility with where the operands are at, right? You understand? Because what can I do with N7 colon 0? I can put anything in there I want to, right? You understand? And then we have indexed addressing. What's indexed addressing? I'm listening. Anybody remember? So these instructions, a lot of your data manipulation instructions use index address. We identify index addressing with this right here, and then we'll come up and we'll identify a register, and then this would be index address. So if I put my address inside of brackets, then it indicates it's indirect addressing. I forgot to see. If we put this, if we get it with a hashtag, it indicates what? So our stack instructions are going to use indexed addressing. Our bit shift instructions are going to be, bit instructions are going to be using index addressing. Our stacking, I said stack. Our fill instructions are going to be using index addressing, right? Y'all understand? Makes sense? So it's important that we understand this. So what is indexed addressing? Let's see if I explained it in these. I know we've already explained it. So notice this guy right here. I come over here. As soon as I see that hashtag up there, it means it's using what? Index address. Everybody okay? So what is index addressing? In fact, I don't even know if the guy even tells y'all what index addressing is, even though we use it exclusively for these instructions. So does he tell you what index addressing is inside this chapter? Don't want to do that. on manual. So when we look at the actual data book, the actual instruction set manual for the Allen-Bradley processors, every time we go to an instruction, it brings up this little file right here, or this little table right here. And this tells us what source A can be, what source B can be, what the destination address can be, what function files are available. But right here, what does it tell us right here about that instruction? What addressing modes we could use for that instruction. So according to this, for this one right here, I can use what? Immediate, direct, immediate. The 1100 does not support indirect address. These instructions, it tells you what we can deal with. We can deal with a what? A word, a long word, and then not a bit, an element. So what we need to do, if we're going to understand these instructions, is we need to understand the addressing mode, right? Yeah, this guy here does it weird. So let's look at the 500 manual. Oops, it's the 1500 manual. Here's the 500. What's that? What? Logical address, word address, and index address. So it says on the index addressing mode, we use a what to specify it as an index addressing. Then we have to provide a what. So the index register is S24, and an offset value in S24 as the status file. All index instructions use the same word, 24, to store the offset value. The processor starts operation with the base address plus the offset. You can manipulate the offset value in your ladder diagram, ladder logic for each index indexing instruction. Another thing that we learn is that a lot of our instructions that use index address, it automatically increments that register for us. Let's see, I got a So this is a bit shift left instruction. Okay. And it's using what addressing mode? Index addressing. So on the bit shift instructions, we got to do a couple of things. We got to come up here. If they all use index addresses, so if I came up here and put B3, you entered it, it would automatically put the hashtag. So bit shift instructions automatically use index address. Then instead of using the status register bits, it uses a control register bit as its status register. Then what we do is we specify where the bit is coming from that we're going to be shifting. Can you see what I'm specifying? Input 3 bit what? 15. And then I can specify the length. What have I specified? 32 bits, a double word. So what's got to happen is this shift's got to automatically go from the first word over to the what? Second word. Well, how is it going to do that? Well, it's using index addressing. So what happens, it automatically gives the index register an offset when it goes to the what? To the second word. Everybody understand that? So let's bring this up and watch it happen. Oops. So we got a stop station, right? So right now it's stopped. Oh, I need to go to run. Okay. By the way, for some reason, and what the advantage of it, I have no idea. But when over in Germany, when they set up a 3-wire control, they put the stop button on the right of the action circuit. Normally over here, we put the stop button on the left on the L1 side. Now, why they do it over there, they couldn't explain that to me, but that's what they do. So we're going to start this, and we got a timer running that's controlling the shift. Okay. And then what we're going to do is we're going to go in and just so I'm shifting in a 1 right now. I can come up here and change that any time. That's just a demonstration of what this thing does. But what's so neat is when it gets down here to 16, watch what it automatically does. It automatically moves over to the next word. How in the world did it know to do that? Well, it's using indexed address. So it has an offset. So what happens when the bit shift left gets to 16 or 15, it automatically adds an offset of 1 and moves over to the wall, to the next word. I don't have to tell it to do that. It automatically knows how to do that, right? Y'all understand that? So we could set up this thing here. Of course, I'm having to do it kind of strange because this output port is 2, this output port is 4. So I'm using a move instruction. After I do my shifting, I'm moving my move instruction to take B3 1 and move it out of this port, and then B3 2 out this port, right? So I'm doing that because the way the input ports are shifted. But this thing will automatically start over. It knows once it gets through the 32 bits, it'll reset it and start over at 0 again. And so we could use this, by the way, to do what? We could, I got 54 motors on a conveyor line or something like that, and I want to sequence start those things. Then we could do that with how many instructions? Very few, right? Y'all understand that? Very few instructions could be taken to sequence start something, to sequence stop something by using the shift left or shift right. If I wanted to sequence stop something, I would use the shift right. If I wanted to sequence start something, I would do the shift left. Well, it depends how I want to sequence stop it. So this thing will run forever. And right now I'm just shifting 1s to there, right? You understand? So when it gets to bit 15, what does it automatically do? Well, it automatically goes to the what? The second word, because it's using indexed address. So there's some instructions that automatically do the offset for you. The copy instruction is one of those instructions. So the copy instructions, I load the index register with what, so here we're loading the index register with B31, I'm sorry, we're loading the index register wherever the chip's at. I'm not using B30 because B30 is using my ceiling circuit. Then I'm clearing it out, right? Every time I stop, I'm clearing it out. So if I hit stop, notice what happens. So here's an instruction, clear. Clear is a neat instruction. What can we do with clear? We can set up, we can clear a bit, or we can clear up an old word, right? You understand that? So I'm using these, and then when I say B31, then I set up my index register to point to what? Whatever B3 location 1 is my index register. And then if I come up here and look at that, so if I look at the register files, so here's the bit files. So you can actually see it shifting through here to that. And then when it gets to 15, what automatically happens? Should do what? Should go to the next one for us. But I could keep going. I mean, I could do a what? I could do a 24-bit shift. I could do a 64-bit shift if I wanted to. And using indexed addressing, it automatically does what? It automatically goes to the next. So look what it did on B3. It automatically set it to what? 1, right? So this is my index register. Everybody okay? This makes sense now? So what index addressing does, it allows us to set up our own stack using first in, first out, or last in, first out. It also gives these instructions that need to go through multiple words. We can do it real fast without having these specified. So if I looked at the Allen Bradley, where they wanted to clear out those memory locations, they used it with one field. They used it with one field instruction. But they used what? Indexed addressing, right? Understand? Siemens doesn't basically support that. So when I cleared out my memory, I had to use a move instruction for three move instructions to do the same thing that I could do with the Allen Bradley. I'm using index addressing. So index addressing, what we do is we start off with an index register. That's basically, so this is what you're defining right here. You're defining the location of the index register. Everybody understand that? And then what can we do from that register? We can offset through that thing any way we want to. Right? You understand? Does that make sense? So what it does is it gives the program the ability to automatically sequence through addresses. But I can also access that thing, right? You understand? By specifying the offset. Are y'all okay? Yes, no? So everybody okay with the move instruction? So what's part of the move instruction? Everybody okay? We've used that before. What's the parts of a move instruction? Yeah, source A and source B, right? Or I'm sorry, source A. Let's bring up a move instruction. Yeah, so only thing we got on a move instruction is a source. Where's the information coming from? And the destination, where we want to put it at, right? Everybody okay? We could move from one register to another register. We could move immediate. So we could come in and we could move 0 into a location. We can move FF into a memory location. So what we can do is we decide the destination address is going to have to be in addressing mode, right? We can use immediate addressing. We can't use immediate addressing. It's got to be what? It's got to be the direct, indirect, or indexed address. So here's our move instructions right here. So when I bring in a move instruction, this is what I got to decide. I got to decide where's the information coming from and what are we putting there, right? So if I wanted to go ahead and clear out a memory location, I could put what? I would use immediate addressing, right? You understand that? And then I could come up here and then I could identify what memory location I wanted to put this in. So your destination address can never use immediate address, no matter what instruction. If it's got a destination address, it's going to have to use another addressing mode besides immediate. I could come in here and do this. You know, I could come in here and take what the contents of N70 and move it into B3. So your source A can either use immediate addressing, it can use indexed addressing, it can use all the addressing modes that are available to us, right? You understand? A destination address cannot use what? It can use index, it can't use immediate, because that's the address of where you want to put it at, right? Then what they talk about next is what we call move with mask. So what is a mask? We talked about this when we got into our logic instructions, your ands and your ors. Huh? It is. It's exactly what it is. It is. So that's a good analogy. A mask allows us to make sure certain bits in the operand are either cleared, or make sure certain bits in the operand are set. We use an AND mask to clear bits. We use an OR mask to set bits. Everybody understand that? Yes or no? We use an AND mask to clear bits. We use an OR mask to set bits. Yeah. So if I come up here and got my information for my source, I'm gonna put input. Free dot zero. In RS Logics, you will have to put the 0 out there. Logic Pro lets you get by with it. And then the math. What bits do we want? What bits do we want to come through from that input right there? Okay, so Bernard said just the even ones. So what we'd have to do is we're going to have to come up with a mask. And it's easiest to come up with a mask using hexadecimal instead of trying to use decimal. You could come up with so if you came up with a mask, you would have to come up with a binary number. So here's what we're coming in. So we're bringing in 16 bits. And these can be anything. And Bernard says he wants to mask off the even bits. So if I wanted this bit to come through, I would put a 1. If I want to block it, I'd put a 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Which in hex would be 5, 5, 5, 5. In decimal, I would have a problem with it. I'd have to come back and do it, right? You understand that? So this is where we need to understand. This is one of the main reasons we need to understand how to go to binary and how to go to hexadecimal. Right? You understand that? To set up these what? These masks, right? So what I would do is I would come up here and it won't let me. So I'll come up here and I'm going to use a move with mask instruction. So here's my move with mask. I'm getting it from this input. And down here under my mask, I'm going to put 5, 5, 5, 5, and I'm going to put an H out there, which tells it it's what? Hex. Now the actual decimal number, it went ahead and converted that to me to 21,845. So I could have took that binary number and converted it to decimal and entered 21,000, but that would be so hard to do, right? You understand? Let the PLC do the work for us. Where do we want to put this at? Well, so we can get a visual representation, we'll come out here and we'll put it in output. Where's one output for? I think I use a comma. Okay. So this is going to be, we have no control devices, so this is going to happen as soon as I input what we want to do, right? What I'm going to do is going to take these outputs and I'm going to change them over to all switches because that'll be easier to do that way. And then we'll download it. And then we'll switch it to run. So we'll close the switch and notice the output went to 1. I close this switch and nothing happened. Why? Because we mask it off, right? You understand? I close this input, it goes through. I close this input, it's masked off. I close this input, and you can see what's happening. So what I'm doing is I'm letting only the watt come through. I'm only letting the odd bits come through, and I'm masking off the even bits. You understand? Yes or no? That kind of confused them all.
Even the even ones come through.
Yeah, because you said you wanted. I said you wanted to mask off. You said I said which ones you want to mask off? You said the evens. So what we're doing is we're masking off the even bits. So what I can do is I can load an input port. I could come up with a math operation. I could any type of operation I want, compares or anything, and then I can strip off what bits I want. I'm not interested in. So we can deal with a whole word, right? You understand? So Allen Bradley's got two options. You either can deal with a bit or you can deal with a word, right? You understand? Or you can deal with a long word. I'm sorry, it's got 3 options. Siemens, you can deal with a byte, you can deal with a word, you can deal with a long word, right? You understand? Just by specifying with the instruction. So here we got bits, we got words, we got long words, right? You understand? But if I was interested in multiple bits, then I could bring in a whole word and then I could strip off what I don't want. So instead of going out and using several input instructions to bring in individual bits, I could bring in a whole word and do what? Just strip off the bits I don't want. And we could strip off the middle 3 bits, the last 3 bits. We could strip off the upper byte. We could strip off the upper byte. I could take this bit out if I wanted to. I could take that bit out if I wanted to. And just strip it off. Now, if I use an OR mask, then we would get 1. But the move with mask, the only mask you have available with the move with mask is the hand mask. If I wanted to OR, then I would have to use an OR instruction.
Hand mask clears the OR method.
Set bits. We make sure we set bits that we won't set for any reason. You say, well, what reason? It don't make any difference. Eventually, you might not never use it, but then again, you might have to use it, right? You understand? Just like that first pass bit that we were looking at. You might not ever use it, but then again, you might not. And then once I saw it, I've never seen it before until I got into the Allen Bradley programs and saw it there. So I started doing a little research, and then all of a sudden it made sense why you would need to use that. So anytime you want to configure something in a certain setup, every time you switch your PLC to run, then you could use what? You could use that first pass bit, and it would automatically you could make it run a subroutine or clear out memory or do whatever you wanted to. But it only happened when you switch to what? When you switch to run. And it makes sense to me now that I found that, even though the book doesn't cover it. So we can't cover everything in this class, but we cover enough to give you a foundation so you can do your own research and go out there and figure out how to do this stuff, right? Like Thomas was talking about, why don't we teach the RS Logic 5000? Why don't we teach the RS Logic 5000? Because we only got 5 PLCs that have the ability to run it. But what we do, if you learn the 500, then what? There's so many similarities to them that you would be able to adopt it. And like I say in robotics, it's one of those, okay, that's how they do that, right? Okay, that's how they do that. Plus they get different features that they add, like the libraries, which RS Logic 500 does not support. Are we okay? So move with mask. Everybody okay? Okay, so what's next? Let's see, moving mask. Then this is where we can actually use our stack. It's kind of simulating a stack. It uses index addressing. We got two methods we can get information off a stack. So a stack is exactly what it sounds like it is. It's just a stack of information, and it's a data table. And we got two ways we can get that information off. Once we stack it up there, we can either pull it off the top or we can pull it off the bottom. That makes sense? So what we have the ability to do is we can stack up a bunch of information. And these are going to be operating, these are going to be in a data file somewhere, right? Y'all understand? And then I got the ability to get the information off the stack. What two ways can we get it off? First in. So if I use that one, it's going to pull it off from the bottom of the stack, right? You understand? If I use the last in, first out, it's going to pull the information off the top. Everybody understand that? So it all depends on how you want to get that information off the stack and how you want to, and of course, putting it on, you just stack it up. Concept of storing and retrieving pallets is similar to the way data is stored on a stack. A stack, I like to use restaurants. When you go into these restaurants and they got these plates, and they're down inside a hole, right? You understand? Of course, that would be last in, first out, right? You understand? So that would be like you stack it. This other way would be like, you know, a lot of vending machines. You go in there and you hit that button. So they stack those things into those little curly springs, right? Well, that would be a last in, first out, right? So they have the ability to go in there and put all those things, just stack those things in there, and then when you enter your money and press a button, the last that the vendor put in there would be the first to come out. Well, those are pretty good information, analogies that y'all run into all the time. So a stack in a PLC or computer terms, a group of consecutive data files or words placed temporarily in a memory location or a go-between, or what we call a block. Everybody probably tell the time too, right? Been over 5 minutes, right? First in, first out, last in, first out. Are we okay there? Everybody okay? Okay. Concept of storing and retrieving pallets. This is what they're doing, but we can use, there's a lot of applications for this, or we can set up tables. We could set up a sequence of addresses that this guy would automatically go through for us. And what addressing mode do you think they use? Something that can automatically go through sequence, indexed addressing. Stacks grows larger as data is pushed onto it. We call it pushing, popping, placing information on the stack. We have different terms. So what I learned is when you push information on the stack, you call it pushing. When you pull information off the stack, they call it popping or pulling. People like to call it popping because it sounds a lot better. So this is an example in your textbook that deals with storing or pushing stuff onto the stack, right? But what we got to understand, a FIFO stack is the first in, first out, right? So we would actually pop from the bottom of the stack. Everybody okay? And then a LIFO stack means whatever you push. So we start pushing information, it pushes it on the top. A, B, C, D, E, F, G, H, I, like that, right? Understand that. And then how we get them. So how we put information on the stack, we got one method. That's from bottom to top. How we get information off the stack depends on which pull or pop instruction that you use. Everybody okay? That makes sense? So what instructions do we have? We have FIFO, first in, LIFO, push operation, pop operation. Are we okay? These are our instructions. Oh, I was wrong. It looks like we can load it from the log. So we can fill and we can load. We'll look and see how those work. but then when we pop it, we're gonna use the wattage unload. So okay so far? Yeah. Yeah, so PLC stacks are created when the stack or the integer word are stored in the memory buffer. Data can be transferred into registers or another memory location from the stack. Okay, so here, the example they're using, they're going to use a counter, and we're using a first in, first out field, right? And then we're using a first out, first in, first out unload. Okay? And what's the length of our stack? So what you do is you specify how big the stack is going to be. So how many are they setting up this stack for? Yeah, 3 words, right? Everybody okay? Yeah, 3 words. So we're pushing the contents of accumulator A, counter A, accumulator A. So remember, Allen Bradley basically don't let us deal with bytes, right? What does it deal with? Words, right? Or long words. Are we okay? The results of what's going on is going to be in register 6. So we'll look and see how this affects. So this is the control register. So what do you know? One of the things they're going to put in the control register is, of course, how long the stack is, or how deep it is, whichever way you want to say it. So the actual program that we have is wrong button. For some reason, my computer won't let me bring up my taskbar. So here we're using a counter, and then we're going to push the contents of the counter onto the stack, and then this instruction right here is going to do what? Pull it, right? Everybody okay? Yes or no? What? B3. So when we go out there and look at the stack, we'll go up here and go to our register with RS Logic. On Logic Pro, it's a symbol. It don't have the little hammer and the little wrench up there. I'd have to go back and look. It's obvious. It's up here on your toolbar on where you can go and actually look at these data registers when something's going on, right? But it's still up in here. Also, when you enlarge on RS Logic 500, it enlarges the whole drawing. The only thing that this enlarges is the text. See, the text get bigger. That's the only thing they do on Logic Pro. But it's still real good in that we can deal with things real fast without trying to program in there, because all of them is built. All your diagrams in the book are in a package that we get. Okay, so we downloaded. We're going to run, and so right now, supposedly we can come up here and take our counter, and we can put anything we want to in it. This would have been good to use switches. So we'll put like a 6 on there. And then what we'll do is we'll go over here and look at our data file. And we're using 0, right? Okay. Yeah. So supposedly when I come up here and push this, it's going to take that 7, and we're using 3, 1, 3. So we need this guy right here, right? When we come up here and hit this, oh, it's input 1, bit 3. Huh? No. Oh, I'm sorry. Wrong program. So this guy here should shift it. So you see that the 7 went into what? Went into bit 0, right? Okay, we're okay. Then I could come up here and I can put something else in here, whatever we want to put. We could go up to 1,000. It'd been easier to use one of our input ports. And then when I come up here and hit 3 again, it's going to automatically do what? So it left this one alone. So what it's doing here, since this is a first in, first out load, right? This was first in. So what did it do? What this guy's doing is shifting the stack down. So it's starting at the top. Whatever I put in there first stayed there, and the stack is moving what? It's moving down. So a first in, first out load instruction is going to run the stack from what? Top to bottom. So we can come up here and put everything, anything we want to. So let's do some more counting. And then I hit 3, and notice the 7 stayed there. Then everything did what? This section stayed there, so the new information is going on the bottom of the stack. Now we're using a first in, first out. So when I execute switch 4, what we should see is the whole stack is automatically going to shift what? Up. So it should pull, this was the first in, so it should be the what? First out. See that? So it automatically pulled that out, right? You understand? Then I'm going to come up here and do it again forward. And then now the stack is empty. And we would have just set a bit in our control register that indicated that I've got to the top or the bottom of the stack. Everybody see that? Well, well, no, the only depth we got is 3. So you establish a link, but yeah, if I put 15 up there, then what I've done is I've set up 15 addresses for my stack. You can't let your stack run errant, because you could definitely get into a problem and you could wipe out the whole memory. You could actually use the whole B3 register if you let this thing run away with you, right? So we specify one of the things we need to do before we use the stack in these first in, first out, these instructions, is first identify how many words do we need. How many words do you need? And then if you exceed that, then it's going to probably give us an error in our R6 register that we can do what? That we know that we tried to overflow our stack. That makes sense. It's like email. They set limits on email. Man, email could flat wipe out a certain. They don't have any limits set here. So they had to dedicate a big server for nothing but our email. Because who never erases their email? Well, I erase a lot of the mass stuff that comes out. But email from anybody here at the college, I never erase it. And you can't believe how many times that saved my butt from getting in trouble. Where you have some people claim that you say, well, you sent that me, and they said, no, I never did. And you go back and pull that up. You know, that's helped me a lot. So there's no telling how many bytes of data they're running on their email, just the email service for here at college. For the instructors, I'm sure, and that's one of the reasons they took the student email off our server. So y'all's email is not on our server yet. Gmail hosts y'all's, but I'm pretty sure they have a limit set on y'all, right? If you're on Gmail, I'm pretty sure. We host the instructors, the instructor's email is hosted here for obvious reasons, you know, but there's no telling how big those are. But so first thing you need to do when you set up your stack is what, Brandon? Decide what? How big you want the stack to be. Now we can change this. I mean, all I'd have to do is to do what? So I could take it off program and I could come up here and just increase that number to 5. Now if I push with 5, notice what happened as soon as I changed this to 5, what did it do? It automatically changed the pool to 5. So, you know, you don't have to worry about the pool, and you can understand why they do that too. So what we're doing, it would be awful if I could push 15 bytes on there, but I could only pull 3, right? You understand? So now we should be able to go back up.
Position is the number of stacks that.
Yeah, that's the number. The position is where you're at inside that stack. So right here. So in these two right here, I'm setting it position. So this is my offset right here, guys. This position, this is my offset. This is what we're offsetting from that index register from. Is by this. So right now I'm offsetting by what? 0. And then I come up here and push that onto the stack. What are we pushing with? 3. Oh, I gotta go back to run. Okay. No, what did it say? Oh, we had to download it because we made a change. So I'm going to come up here and push it now. Now we're dealing with 32. And notice it automatically did what? Incremented the position, right? You understand? On both, not only your field, but also not only your push instruction, but also the pop. So yeah, and we could keep doing that, you know. Then load it. But now what's going to happen is we have the ability to go through how many, so our stack would be five words long, yeah. And like I said a while ago, and you can do this on RS Logix too, or Logic Pro, RS Logix 500. You can actually bring up the B3 or wherever you put this at. Now we're using the B3 register. So back there on one of the tests, and it said the B3 register is used, and in the book it says the B3 register is used by internal relays. That's false. We can use that B3 register for anything we want to, right? We can use the N7 register to store things. It's just that if I stored a number with a fraction into one of our integer registers, it would strip off the fraction portion, right? We can use our floating point register. I can use my floating point register as a stack. So if I wanted to go out there and I was saving numbers that had decimal points in it, then I would want to save that information in the stack too, right? You understand all that data. So saying that the B3 register is used only for internal coils, which the guy, I can almost go back and find that in the chapter, that is not what. True, we could say it's used primarily for internal bits, internal coils, but we can use that register for anything we want to. Here we're using it as a stack. But I should be able to, let's see if we can do that. Just let's see if this guy lets us do that. So let's go back and let's move our stack over to N7. And we'll use N7:0. And then we'll have to pull it off of what? N7:0. So here we're using index addressing, but we're set our stack up to be located in one of our N data files, right? And then we'll download it and we'll see if this works. So I've got 42 on there and we load the stack with 3, right? Okay, so see it did what? It did exactly the same thing, right? Y'all understand that? So what we have the ability to do is any data file you can use for about anything you want to, right? What can I do with one of my input data files? I can read information from it and I can store information into it, which we wouldn't do because it would change instantly. So I can read from an input data file, I just can't write it. So it would be what we call a read-only data file. I can write into my output register and I can read from my output register. So your output register is a read-write file. The input, it should be obvious why it would be a what, why it would be a what we call a read-only. But yeah, I could store the results of this math, and I could take the results of a math operation and store it to an output word. And then my output ports would do what? It would correspond to the results of the math instruction, which is pretty interesting. So this is a first in, this is a first in, first out, right? And what's the next one we can use for our stack? We could use the last in, first out, right? Last in, last out. And that should be,
Last in, first out.
okay. So let's go back and load the next, what's the next example in the textbook? What's the figure number? Okay. 14, 7 or 6? I think but 6 was the one I was using. So this is the last in, first out, LIFO. We're set up to use the D3. Now they're using word 10. But we're going to start at word 10. So we were starting at word 0, but now they're starting at word 10, right? So we could literally combine these two programs inside the D3 register. Here, they're sending it out. Here, we're doing a little difference. We're sending it out where? To the output port. Was it doing it on the other one too?
Yeah.
No. So we should see our lights over here responding. I didn't even notice that guy, but we're over here on output 4 is the one they're using, right? So your destination can be any data file, right? You understand that? Using any of the addressing modes that's available to you on your PLC. What addressing mode are we using? Yeah, no, here for our destination. Direct, good. Yeah, we're using direct address. So here, we're not using a counter. What are we getting? Oh, I'm sorry. We're getting, now here, we're getting this from an input. We're getting it from input 3, which is this guy right here. So what's nice about this is I can just come up with any number I want to. So we'll just randomly come up with something. And then let's download it, and then we'll run it. So what we'll do here is we're using 5. It's this guy right here, and we're using 6, and we're using 7, and we're using 9 to reset our status register. So let's look and see what's going on. Does the book tell us what bits in the status register are used? Or not the status register, the control register. And so we're using input 7 and we're using input 9. We're not using input 8, are we? Okay. So I'm going to bring up my, so here we're bringing them directly in. So our stack is at B310. So here's 10. So we're in run. And I've got this up where I can't get to it. Okay, so B310. So let's so I can't do what now? I can't move it and I can't close it. Yeah, it's got stuck up there. Yeah, I can't, it won't let me close it right here. So I gotta hit the button up there. Huh? Yeah. So I can stick it here in the center, I think. So, so 5 is going to push it on the stack. Yeah, it's starting at 10. And I've messed up. Phil, I mean, that's pretty explanatory. So Phil uses index addressing. So what does Phil allow us to do? Yeah, so blocks of data. So if I wanted to clear out a bunch of memory locations before I started, you know, I'm saving all this information out there in my memory, and
I hit reset on my machine. Well, what do you want to do? Odds are, if you want to reset something, you want to go back, do what? Yeah, you want to go back and do what? Maybe you want to fill your output ports, right? You understand? You want to clear all your output ports when you hit reset. Well, I could use move instructions, right? Or wouldn't it be nice if I could go out there and just fill all my output ports with 0? Right? Right, you understand? So, fill all my output ports, or if I had a data file out there that I wanted to pull in and set it up a certain way, I could do it that way, right? You understand that? So fill allows us to come in and just fill information. I could set them all to 1s, I could set them all to 0s, I could set them all to whatever one I wanted to do. So fill allows us to fill consecutive memory addresses with whatever information we want to put. It would be a source and a destination. What address and mode does that use? Index. So what do we need in the fill instruction, guys? What's in the fill instruction? What information is the fill instruction? So it's very similar to the stack instructions, right? You understand? But source, what's our source? What address and modes do you think we could use for our source? Yeah, all 4 of them, right? If I wanted to fill with 0, then I would do what? I would use immediate address. But if I wanted to pull the contents off a memory location, I could set up any memory location I wanted to, and I could fill memory with that content. Yeah, you'd put 0 in the source, right? And then you'd put the starting address you wanted to start filling, and then you would put the number of bytes that you wanted to fill. The number of address, the number of consecutive words that you want to fill. Okay, you understand? Right. They used it in the Allen Bradley programs. They didn't have to use it the second time, but they used it the first time. Oops. So these are the actual Allen Bradley programs that's running the Festo line over there. So I'll just bring up the one that we've been playing around with. This is running the distribution station, which is it says it's already loaded. And what we're going to do is look at this blank. Oops, not blank, I'm sorry. We're going to look at the stop. So automatically, when they stop, what do they do? Of course, I know y'all understand German.
Yes.
But they also put it in English, probably. So what's the first instruction doing? So every time you go up there and you hit the reset button, this is what they're doing. When you hit the reset button on the front of that thing, you hit stop, reset, it goes out there and runs this subroutine. And what's the first thing it does? It clears out all your bit files that you're using for internal calls. Okay, it clears them all out. They're out there. Then what does it do? It could have used the move, they could have used the move instruction here, but he's using a fill, right? So what are they filling? They're filling output, output 0.0, word 0, and they're filling it with what? 0. So what that's doing is going to turn off all those output ports. But they're only doing one word. The programmer could have used the move instruction for the second.
Okay, but bit 3 words.
Yeah, 3 words. And that's all the bit files they're using. So if we went back and looked at the auto program, which is using all the bit files, you notice they're using word 0, they're using word 1, they're using word 2, if we get on down here. So these are all these bit files that's being used as internal relays, right? Latch and relays. Well, instead of me going out there and try to reset all those things, what does it do automatically? We'll go out there and reset all those bit files. Then they do what? Then they go back and reset all the output ports to 0. They turn all the output ports off.
That was just one word out.
Yeah, one word. And like I said, they could have used a move right here. They could have used a clear instruction. But undoubtedly, that's what they had in their mind. So we had several instructions. Since this guy right here was only one word, they could have cleared output port 0. So we have a clear instruction, which the book doesn't talk about, but the clear instruction only clears, you have a source and you have a destination. It'll clear out one word. The clear instruction will. The move instruction only sets up one word, but the move instruction, you can put anything you want to in a move instruction, right? You understand? Fill, you can use anything you want to in the fill instruction. Well, what the fill instruction does, it automatically will take you through consecutive words, because it's using indexed address. So here they could have used what? They could have used a move instruction, or they could have used a clear instruction. And but they decided to use the fill instruction, but they're only filling how many times? How many words? Yeah, one word. Now, anytime the PLC pulls information in from an input port, it assumes it's binary. Y'all understand that? But I don't deal with binary. I deal with decimal, right? Y'all understand that? So what we need to do, if I do math, the math cannot be on BCD. The math has got to be binary math, right? You understand? Because everything that the PLC brings in, it considers it to be binary. Even though you think even though you say, well, how does it not know? Well, it just assumes everything is what? So we need to have instructions that we can do what? Oops. We need to have instructions where we can actually go out and tell this guy RPM display. Here we go. So this is one that I wrote. And this is the last thing they cover in this chapter. So copy file does exactly. Copy file allows us to move multiple bytes of data. So if I had like an error message, a table of error messages that I wanted to send to a display, then what we could do is we could just take a block of memory and copy it from this location to that location. So what it does, it allows us to copy multiple locations, right? So a move instruction is just going to move one source over to one destination. The copy allows us to move multiple sources over to multiple destinations. So it uses index address. So what I'm going to do is I'm going to move over to this one. So let's go ahead and download this. And what I'm going to do is I'm going to move over to my data switches. So when I input information from these data switches, notice it only goes from 0 to 9. If it was hexadecimal, it would go from 0 to L. So these are BCD data switches. Normally we used to call them thumb wheel switches, where you got these thumb wheels, you go up here and dial in the information. Some of them use push buttons like this. So you come in and you set any number in here you want to. But the problem is when it comes in, so I can see I got 509. What does my PLC see it as? Yeah, 1,289, because it's converting that to binary. So if I took 0509 in hex and converted it to binary and added all those 1, 2, 4, 8, 16, 32 together, it would come up and give me 1,289. Are we okay? Okay. Then what we're going to do is take that and move it into a bit register. So I'm gonna come up here and, it's already been moved, right? Into destination here. This is what I'm gonna do now is I'm gonna come up here and put in another number. And then I'm gonna hit my one switch. And it interpreted that as what? So it says 809, but it interpreted it as at what? 2057. Okay. Then what I'm doing is I'm taking those two words that I stored it in and I'm using the FRD instruction. What's the FRD instruction? It's going to take the BCD, it's going to take those ones and zeros and convert it into binary form. Everybody understand? So notice what happened here. Time for lunch. Oh, I hadn't done it yet. So I'm going to come up here and hit switch 2. Switch 2. Okay, so look what it's got down here. It's got what? Okay, it's 809, right? You understand. And then it's taking my other number, which is equal to what? No, something's wrong. Let's reload it. Switch 2. Switch 2. There we go. No, it's still not right, is it? I don't know what's going on there. See, it's seeing is what? Yeah, it's for some reason it's seeing this input wrong. So it saw this one up here okay, right? Oh, I'm sorry. See if it's right down here. Okay, so it is. So let's redo that. And this worked perfect last time. Can you see can you see the problem I'm having? So I come up here and put my first number in. So what I'm supposed to do is put the first number in. And then I can move that. Right? You understand? And it saw it as 787. And then I'm supposed to come in here and move my second number in. And 1. Huh? So what I'm trying to do is I'm trying to do math on two 4-digit numbers without exceeding the range. So what this does when I bring it in, it sees it as, so here's input 5. So notice what it sees it as. It sees it as binary, right? Even though it's these 6. So there's 0. But if I come over and click that one, it thinks it's 256. Okay? Because if I converted this over to binary, it would be 256, right?
You understand? You okay? What's happening when I come up here and push this button, it's supposed to take that value, which is 256, and put it in this address. Now, what I'm going to do next is I'm going to come up here and I want to go to the next address, and I can come in here and put in another number, which is saying it's 369, right? You understand? And then when I press 1, it's going to take 369 and put it in there.
That's 0.
Yeah, so this is 256, right? You understand? And this is 369.
Yeah.
And then what we're doing is we're converting that into binary. And then we're taking that and doing math with the binary number, right? Y'all understand? And then what we're doing is we're converting it back to BCD, and we're going to output this to output, which is wrong. So the two numbers that I added together were not the same. You understand what I'm saying? So something's going on with the RS Logic. Y'all go ahead and go to lunch.